JEP 431, Sequenced Collections. Summary. Introduce new interfaces to represent collections with a defined encounter order. Each such collection has a well-defined first element, second element, and so forth, up to the last element. It also provides uniform APIs for accessing its first and last elements, and for processing its elements in reverse order. Life can only be understood backwards, but it must be lived forwards. Kierkegaard. Motivation. Java's collections framework lacks a collection type that represents a sequence of elements with a defined encounter order. It also lacks a uniform set of operations that apply across such collections. These gaps have been a repeated source of problems and complaints. For example, list and deck both define an encounter order, but their common supertype is collection, which does not. Similarly, set does not define an encounter order, and subtypes such as hash set do not define one, but subtypes such as sorted set and linked hash set do. Support for encounter order is thus spread across the type hierarchy, making it difficult to express certain useful concepts in APIs. Neither collection nor list can describe a parameter or return value that has an encounter order. Collection is too general, relegating such constraints to the prose specification, possibly leading to hard-to-debug errors. List is too specific, excluding sorted set and linked hash set. A related problem is that view collections are often forced to downgrade to weaker semantics. Wrapping a linked hash set with collections unmodifiable set yields a set, discarding the information about encounter order. Without interfaces to define them, operations related to encounter order are either inconsistent or missing. While many implementations support getting the first or last element, each collection defines its own way, and some are not obvious or are missing entirely. First element, last element. List.get0 list.get-list.size 1 deck.get first deck.get-last sorted set.first sorted set.last linked hash set.iterator. Next / missing. Some of these are unnecessarily cumbersome, such as getting the last element of a list. Some are not even possible without heroics. The only way to get the last element of a linked hash set is to iterate the entire set. Similarly, iterating the elements of a collection from first to last is straightforward and consistent, but iterating in reverse order is neither. All of these collections can be iterated forward with an iterator, the enhanced for loop, a stream, or to array. Iterating in reverse is different in every case. Navigable set provides the descending set view for reverse iteration. 4. var e, nav set.de sending set, process e. Deck does so with a reverse iterator. 4. var equals deck.de sending iterator, it dot has next. var e equals it dot next, process e. List does so but with list, iterator. 4. var equals list.list iterator list.size, it dot has previous. var e equals it dot previous, process e. Linked hash set, finally, provides no support for reverse iteration. The only practical way to process the elements of a linked hash set in reverse order is to copy its elements into another collection. Similarly, processing a collection's elements using streams is a powerful and effective alternative to processing elements using loops, but obtaining a stream in reverse order can be difficult. Of the various collections that define encounter order, the only one that supports this conveniently is navigable set. Navset.de sending set. Stream. The others require either copying the elements to another collection or creating a stream from a customized splitterator that reverses iteration. This is an unfortunate state of affairs. The concept of a collection with defined encounter order exists in multiple places in the collections framework, but there is no single type that represents it. As a result, some operations on such collections are inconsistent or missing, and processing elements in reverse order ranges from inconvenient to impossible. We should fill these gaps. Description. We define new interfaces for sequenced collections, sequenced sets, and sequenced maps, and then retrofit them into the existing collections type hierarchy. All of the new methods declared in these interfaces have default implementations. Sequenced collections. A sequenced collection is a collection whose elements have a defined encounter order. The word sequenced as used here is the past participle of the verb to sequence, meaning to arrange elements in a particular order. A sequenced collection has first and last elements, and the elements between them have successors and predecessors. A sequenced collection supports common operations at either end, and it supports processing the elements from first to last and from last to first, i.e., forward and reverse. Interface sequenced collection less than E extends collection less than E / new method. Sequenced collection less than E reversed / methods promoted from DEC. Void add first E, void add last E, E get first, E get last, E remove first, E remove last. The new reversed method provides a reverse-ordered view of the original collection. Any modifications to the original collection are visible in the view. If permitted, modifications to the view right through to the original collection. The reverse-ordered view enables all the different sequence types to process elements in both directions, using all the usual iteration mechanisms, enhanced for loops, explicit iterator loops, for each, stream, parallel stream, and array. For example, obtaining a reverse-ordered stream from a linked hash set was previously quite difficult, now it is simply linked hash set.reversed stream. The reversed method is essentially a renamed navigable set : descending set, promoted to sequenced collection. The following methods of sequenced collection are promoted from DEC. They support adding, getting, and removing elements at both ends. 1. Void add first E2. Void add last E3. E get first 4. E get last 5. E remove first 6. E remove last. The add, E, and remove methods are optional, primarily to support the case of unmodifiable collections. The get and remove methods throw no such element exception if the collection is empty. There are no definitions of equals and hash code in sequenced collection because its sub-interfaces have conflicting definitions. Sequenced sets. A sequenced set is a set that is a sequenced collection that contains no duplicate elements. Interface sequenced set less than E extends set less than E sequenced collection less than E, sequenced set less than E reversed, / covariant override. Collections such as sorted set, which position elements by relative comparison, cannot support explicit positioning operations such as the add first E and add last E methods declared in the sequenced collections superinterface. Thus, these methods can throw unsupported operation exception. The add first E and add last E methods of sequenced set have special case semantics for collections such as linked hash set. If the element is already present in the set, then it is moved to the appropriate position. This remedies a long-standing deficiency in linked hash set, namely the inability to reposition elements. Sequenced maps. A sequenced map is a map whose entries have a defined encounter order.
Interface sequenced map less than K, V extends map less than K, V, / new methods. Sequenced map less than K, V reversed. Sequenced set less than K sequenced key set, sequenced collection less than V sequenced values, sequenced set entry less than K, V sequenced entry set, V put first K, V put last K, V, / methods promoted from navigable map. Entry less than K, V first entry, entry less than K, V last entry, entry less than K, V poll first entry, entry less than K, V poll last entry. The new put, K, V, methods have special case semantics, similar to the corresponding add, E, methods of sequenced set. For maps such as linked hash map, they have the additional effect of repositioning the entry if it is already present in the map.
For maps such as sorted map, these methods throw unsupported operation exception. The following methods of sequenced map are promoted from navigable map. They support getting and removing entries at both ends. 1.
Entry less than K, V first entry 2. Entry less than K, V last entry 3. Entry less than K, V poll first entry 4. Entry less than K, V poll last entry
Retrofitting. The three new interfaces defined above fit neatly into the existing collections type hierarchy. Click to enlarge. In detail, we make the following adjustments to retrofit existing classes and interfaces. 1. List now has sequenced collection as its immediate superinterface. 2. Deck now has sequenced collection as its immediate superinterface. 3. Linked hash set additionally implements sequenced set. 4. Sorted set now has sequenced set as its immediate superinterface. 5. Linked hash map additionally implements sequenced map. And 6. Sorted map now has sequenced map as its immediate superinterface. We define covariant overrides for the reversed method in the appropriate places. For example, list::reversed is overridden to return a value of type list rather than a value of type sequenced collection. We also add new methods to the collections utility class to create unmodifiable wrappers for the three new types. 1. Collections.unmodifiable sequenced collection sequenced collection. 2. Collections.unmodifiable sequenced set 3. Collections.unmodifiable sequenced map. Alternatives. Types. An alternative to adding new types would be to repurpose the list interface as a general sequenced collection type. Indeed, list is sequenced, but it also supports element access by integer index. Many sequenced data structures do not naturally support indexing and would thus be required to support it iteratively. This would result in indexed access having ON performance instead of the expected O1, perpetuating the mistake of linked list. Deck seems promising as a general sequence type, since it already supports the right set of operations. However, it is cluttered with other operations, including a family of null-returning operations, offer, peek, and poll, stack operations, push and pop, and operations inherited from queue. These operations are sensible for a queue but less so for other collections. If deck were repurposed as a general sequence type, then list would also be a queue and would support stack operations, resulting in a cluttered and confusing API. Naming. The term sequence, which we have chosen here, implies elements that are arranged in order. It is commonly used across various platforms to represent collections with semantics similar to those described above. The term ordered is not quite specific enough. We require iteration in both directions, and operations at both ends. An ordered collection such as a queue is a notable outlier. It is ordered, but it is also decidedly asymmetric. The term reversible, used in an earlier version of this proposal, does not immediately evoke the concept of having two ends. Perhaps a bigger issue is that the map variant would be named reversible map, which misleadingly implies that it supports lookup by key and by value, sometimes called a by map or BIDI, map, add, put, and unsupported operation exception. As described above, explicit positioning APIs such as sorted set: add first and sorted map: put last throw unsupported operation exception because the sequence of their elements is determined by relative comparison. The asymmetry of having some collections not implement all of the sequenced collection operations may seem unpleasant. It is nonetheless valuable because it brings sorted set and sorted map into the sequenced collection family, allowing them to be used more broadly than otherwise. This asymmetry is, also, consistent with prior design decisions in the collections framework. For example, the map::key set method returns a set, even though the implementation returned does not support addition. Alternatively, the addition operations could be kept separate by rearranging the interfaces along structural lines. That would result in new interface types with very thin semantics, for example, addable collection, that are not useful in practice and that clutter up the type hierarchy. History. This proposal is an incremental evolution of our 2021 reversible collections proposal. The major changes from that proposal are renaming, the addition of the sequenced map interface, and the addition of unmodifiable wrapper methods. The reversible collection proposal was in turn based on Tagir Valeyev's 2020 ordered map/ordered set proposal. Several fundamental concepts from that proposal are still present, although there are many differences in detail. Over the years we have received many requests and proposals in the vein of combining a list with a set or map. The recurring themes are a list that contains unique elements, or a set or map that maintains ordering. These requests include 4,152,834, 4,245,809, 4,264,420, 4,268,146, 6,447,049, and 8,037,382. Some of these requests were partially addressed with the introduction of linked hash set and linked hash map in Java 1.4. While those classes do satisfy some use cases, their introduction left gaps in the abstractions and operations provided by the collections framework, as described above. Testing. We will add a comprehensive set of tests to the JDK's regression test suite. Risks and assumptions. Introducing new methods high in the inheritance hierarchy runs the risk of clashes over obvious method names such as reversed and get. First. Of particular concern are the covariant overrides of the reversed method on list and deck. These are source and binary incompatible with existing collections that implement both list and deck. There are two examples of such collections in the JDK, linked list and an internal class sun.auth.util.identity linked list. The linked list class was handled by introducing a new reversed covariant override on linked list itself. The internal identity linked list class was removed as it was no longer necessary. An earlier version of the proposal introduced covariant overrides for the key set, values, and entry set methods of the sequenced map interface. After some analysis, it was determined that this approach introduced too great a risk of incompatibilities. Essentially, it invalidates any existing subclasses. An alternative approach was selected, which was to introduce new methods sequenced keyset, sequenced values, and sequenced entry set into sequenced map instead of adjusting the existing methods to be covariant overrides. In retrospect, it may have been for the same reason that a similar approach was taken in Java 6 with the introduction of the navigable key set method instead of modifying the existing key set method to be a covariant override. See the report attached to the CSR, JDK 8,266,572, for a full analysis of the incompatibility risk.